Now the tangent ratio, or the tan ratio, is an interesting trigonometric ratio. In fact, what interested me first of all is why is it called the tangent ratio? Where does that word come from? I did create a video earlier on which covers the origin of the words sine, cosine, and tangent, but especially with the tangent ratio, why it's called that. But anyway, that's not the purpose and the focus of this video. I want you to evaluate a few of these. Okay, so I actually come up with just a few examples to start off with. So kind of doing this in reverse, where we look at some examples first, and we try to deduce from these examples some pattern. So sine of 20 over cos of 20. Okay, so in fact I might do these on two calculators again. So maybe put this out of the way. Yep. Okay, so with that bit of a shine there on that calculator. Yep, that's better. Okay, so I might just do this here. So sine of 20 over cos of 20 degrees. Okay, and I might put here, enter in tan of 20 degrees. Okay, press equals there, and I press equals there. And what do we notice? It looks like the same value. It's a bit like what happened in the last video when we looked at sine versus cosine. Okay, so we found that these two are in fact identical to each other. Okay, what about the next one? Sine of 45. Okay, over cos of 45. Okay, and tan of 45. Tan of 45 is 1. Sine of 45 over cos of 45 is also 1. Okay. What about sine of 30 over cos of 30? Okay, so sine of 30 over cos of 30. Okay. And tan of 30. By the way, that's actually 1 divided by the square root of 3. There'll be a video that talks about this as well. There are certain interesting angles, okay, that we'll look at later. Okay, not in this video, but that's coming up. All right. Sine of 90 over cos of 90. I suspect the calculator is probably going to have some trouble here. Whoops, math error. Tan of 90. And also, get a math error as well. All right, something's going on here. There seems to be something going on here between this quotient, sine of theta over cos of theta, whatever the angle is, and tan of theta. So tan of theta must, well, at least from what we've observed, represents this quotient or this division between sine and cos. I had to throw this one in. Okay, if you watched the last video, which is on the complementary ratios. Sine of 15 over sine of 90 minus 15. Now you should hopefully know what sine of 90 minus 15 is equivalent to. Be pleasantly surprised, okay, and do try tan of 15. Who would have thought? Exactly the same answer. Notice this time I didn't use cos or cosine, or did I? Recall that is just the same as cos of 15 degrees. Complementary ratios. All right. So you're both thinking, yes, of course, complementary ratios. Sine of 90 minus 15 degrees is really the same as cosine of 15 degrees. Complement of sine. That co is embedded here. Okay. Anyways, just thought I'd throw that one in. So, looks like there's a kind of a pattern here, okay? And sometimes with mathematics, some of the most amazing discoveries are actually done or sort of found almost by accident or by experimentation. A pattern sort of almost looks evident, and you think, hang on a moment, I think there must be a pattern here. And the pattern here seems to go something like this. That tan of theta, okay, must equal, let's put theta there, sine of theta over cos of theta. Or if you want to write it in linear form, sine of theta divided by cos of theta. Somehow. Okay. Just quickly back to this sine of 90 over cos of 90. And we said we got a math error. You might be asking yourself, why do we get a math error? All right. Again, this will be explained in a subsequent video, but try cos of 90 on its own. It must be something we're dividing it by. Try cos of 90. That's the denominator. Cos of 90. You get 0. Interesting things happen when you divide by 0. Okay, one of them is that one possible answer is infinity. Well, it could be negative infinity. I mean, we want one or the other, I don't know. But anyways, something that's undefined, we don't know what it is. All right, let's have a look at a proof. So why is that? Okay, and we've got an example there as well, just a brief one. Right, very similar to the last video where we sort of proved that sine of theta is equal to cos of 90 minus theta. This time around, we're going to prove that sine theta over cos of theta is equal to tan of theta. Now, we do know from SOHCAHTOA, all right, and our definition of the trig ratios, that tan of theta, at least based on this triangle here, is opposite over adjacent, SOHCAHTOA. So that's going to be B over A, isn't it? Okay, so we know this. This is by definition. So recall this from SOHCAHTOA. We want to prove the point. Okay, so let's define sine of theta. After all, we're trying to prove that sine of theta over cos of theta, or divided by cos of theta, is equal to tan of theta, equal to B over A, the ratio B on A. Sine of theta is opposite over hypotenuse, B over C. What's cos of theta? Cos of theta is adjacent over hypotenuse, A over C. Now, sine of theta divided by cos of theta is really equal to B over C divided by A over C. Now, what do we know about dividing by a fraction? Okay, the second fraction. Okay, really it's the denominator of it's a fraction inside a fraction here. But the second fraction, okay, we invert it, take the reciprocal of it, and we turn the division into a multiplication. So B over C multiplied by C over A. And who could have guessed what's going to come up next? The C's cancel, so they disappear. Go, disappear. And we're left with B over A. Not just running out of space here. B over A is all the way back there. Tan of theta. Okay. So we can now see that sine of theta divided by cos of theta is equal to tan of theta. Over cos of theta. Okay. So there's a sort of a basic proof. Okay. And just one quick example. If sine of theta is equal to 5 on 13, cos of theta is equal to 12 on 13. Find tan of theta. Now, these are just sides of a right angle triangle, of the same right angle triangle, in fact. Opposite over hypotenuse, adjacent over hypotenuse. Tan of theta is going to be opposite over adjacent, isn't it? Right? So I'd expect the answer to be 5 on 12. Well, let's use the definition then of tan. Okay, so tan of theta is equal to, tan of alpha is equal to sine of alpha divided by cos of alpha. Okay, sine of alpha is 5 on 13 divided by 12 on 13. Okay, we invert the second fraction, so we have 5 on 13 multiplied by 13 on 12. The 13s cancel, and we are left with 5 over 12. And that makes sense. If we drew a right angle triangle, okay, the hypotenuse would be 13, the opposite side would be 5, there's our alpha, and the adjacent side will be 12. And we know from definition of the tangent ratio that it's opposite over adjacent.